Hey everybody, Dr. A here, and in this video we're going to be exploring another average normal stress type of problem. So let's go ahead and get started. In the given information, we're being asked to compute the average normal stress in each wire, which have a 1/8 inch diameter. So here we have this figure. We have a weight of 15 pounds that's hanging through this little eye ring, and this load is being transmitted to two wires, AB and AC. And if you see up at B, we have a little external pin connection, and at C, another external pin connection. Wire AB is at a 30-degree angle from the horizontal, and then wire AC is at a 3/4 slope. Okay, so this is kind of a classic physics 1 or statics type of problem, except now we're being asked to find the average normal stress in each wire. Okay, now this is an axially loaded system. The reason why is because you have a pin at B and a pin at C. And so this weight right here of 15 pounds is going to be transmitted or supported by wires AB and AC through axial tension. Okay, so we're interested in the axial tension in AB and AC. And how do I know it's in tension? Well, if you just look at it, the 15 pounds hanging from A, it cannot be inducing anything other than tension in wires AB and AC. So here's what we do. We begin by saying solution, and we're going to say solve for the forces in the wires. Okay, and then from there we can divide those forces by their cross-section areas, and we'll get the stresses in each wire. Okay, so how do we solve for the forces in each wire? Well, we draw a free body diagram of A. Okay, so point A is like a little particle, all right, from statics or physics 1. And you have 15 pounds hanging here. Now, what else is happening at point A? Well, you're going to have a force here. We can call this FAC, and this is at a 3/4 slope. And then you have a force over here in AB. We're going to call this, of course, FAB. And this is at a 30-degree angle from the horizontal, all right? And so from here, what do we have? Well, we have a particle, point A. We have one known force, and we have two unknown forces. So the physics and the statics behind this is the same as what we learned in statics with method of joints for trusses. Although this really isn't a truss, but from a statics perspective, when we analyze point A, we're analyzing point A using the method of joints, okay? So here I have two unknowns, and I need to use two equilibrium equations for that particle A. So the first one I'm going to say is sum of the forces in the x direction equals 0, and to the right is positive. So here I look at everything with an x component. So I'm going to say negative FAB times the cosine of 30 degrees plus FAC times the sine of this interior angle. Now, do I know that interior angle directly? Well, not really, but I could get it. I could say arctangent of 4/3, and I could get that interior angle. But because I know that this is a slope ratio of 3 horizontal and 4 vertical, I know that the cosine of that angle is just adjacent over hypotenuse. So that'll be 3/5. And I'm going to say that equals 0. So one more time, let's explain this. The negative here in FAB is coming from the fact that FAB here has a horizontal component pointing to the left. Okay, and we said to the right is positive. So that's where the negative comes from. Cosine of 30 gives us the x, or the horizontal component of FAB. So if I say FAB, which is this diagonal, times the cosine of 30 degrees, I'm going to get that horizontal force component, and it's pointing to the left, so it's negative. Now on the FAC wire, FAC is oriented at this diagonal direction. If I multiply that by 3/5, that's 3, that's this horizontal ratio to the slope ratio, that will give me the horizontal component of FAC. That'll give me like FACX, the X component, okay? And again, 3/5 is the cosine of this angle, right? Because the cosine of this angle is adjacent over hypotenuse, and this is a 3, 4, 5 right triangle. All right, so there's my first equilibrium equation. Now I have these two unknowns. I need a second equation. So I'm going to say sum of the forces in the y direction equals 0. We can take up as positive. And so here I'm going to have minus 15 pounds. And I'm going to say plus FAB times what? How do I get the y component of FAB? I would say times the sine of 30 degrees. And then I'm going to say plus FAC. How do I get the y component of FAC? Well, I need to say FAC times the sine of that interior angle, which is 4/5, right? Opposite over hypotenuse gives you the sine of an interior angle when that angle is referenced from a horizontal reference axis. And I'm going to say that equals 0. So what do we have here? We have two equations and two unknowns, okay? So I'm going to call this one equation 1. I'm going to call this equation 2. All right? And so what I'm going to do is I'm going to do some algebra here to refresh our memories. I'm going to say, let's solve for, how about we solve for FAB? All right? So I'm going to say FAB from equation 1 here is going to be equal to what? Well, it's going to be FAC times 3/5 divided by that cosine of 30 degrees. Okay? So when I punch this through, I'm going to get 0.6928 times FAC when I rearrange this equation 1 and I solve for FAB. So why don't you pause the video and do that little calculation on your own right now and make sure you get this same value, okay? Now, what we do is we substitute that into equation 2, okay? So I'm going to substitute FAB is equal to this term into my equation 2 here, and I'm going to do some algebra rearranging, okay? So substituting, let's change colors here. Substituting this 0.6928 FAC into FAB and doing some rearranging, what am I going to get? Well, I'm going to say 0.6928 FAC times the sine of 30 degrees plus FAC times 4/5, which is 0.8, equals 15 pounds. I just moved that 15 pounds to the other side of the equation. Okay, and so again, doing a little bit of algebra here, I should end up with 1.146 FAC equals 15 pounds. And so FAC will be 15 divided by that 1.146. So that's 13.8 pounds. And then what I do is I substitute this FAC value, 13.08 pounds, back into equation 1. And I'll end up with FAB equaling 9.065 pounds. And both of these are in tension. So maybe pause the video and make sure you can do this algebra on your own. This is basic algebra 1 operations, and so far what we've done is not even really statics. It's more like physics 1, which is before statics, okay? So now we have these forces, and we can go ahead and calculate the stress in each wire, all right? So I'm going to say the stress in wire AB is going to be the force in wire AB divided by the area of wire AB, and the stress in AC is going to be the force in AC over the area of AC. Now, we were told those diameters were the same, so the area of AB and the area of AC are the same, and we can say that's pi d squared over 4. And we were given a 1/8 inch diameter wire, so that's 0.125 inches squared over 4. And when we crank this through, we get about 0.01227 square inches. And I substitute that area into the denominators of each of those stress values. So sigma AB is 9.065 pounds divided by 0.01227 square inches. So let's see what we get. I get 739.1 pounds per square inch, and I can round that to just 739, and we abbreviate pounds per square inch as PSI, and that's going to be in tension. Okay, both of those forces, of course, like we discussed, were in tension. And then I'm going to say sigma AC is 13.08 pounds, and that cross-section area was the same, 0.01227 square inches. And let's see what we get here. I get about 1,066 PSI in tension. And those are my two final answers. I like this problem because it forces us to review some basic physics 1 and statics. So hopefully you found this problem helpful. If you did, please hit like and subscribe.